Um, Here is some solved problems on the kinematics part. I just meant to kind of review the main concepts of the kinematics part, including the rectilinear motion and the curvilinear motion. I have my first problem here. It says the main elevator A. So we have an elevator A here of the CN Tower in Toronto. Rises about 350 meters. So the total height of this tower here, where the elevator goes up and down, is 350 meters. And for most of its run has a constant speed of 22 kilometers per hour. So most of the run here, the speed is constant, where the speed is around 22 kilometers per hour. Assume that both the acceleration at the beginning and the deceleration at the end of the run have a constant magnitude of 1/4 g. So we have at the beginning we have acceleration, then it reaches a speed of 22 kilometers per hour, and then towards the end it starts to reduce the speed. So we have a deceleration up here. During the acceleration and the deceleration, we have a constant value, which is 1/4 g. Determine the time duration t of the elevator run. So we require the total time duration during the acceleration, the constant speed period in the middle, and then the deceleration. So we can break down the problem into three different parts. The first part is acceleration, the second part is deceleration, and the third part is the run in between, the constant speed part in between. So during the acceleration period, because we understand that the acceleration is constant, so we can apply this equation. We have here a rectilinear motion, so v, which is the final velocity, is equal to the initial velocity plus the acceleration multiplied by the time. The final velocity here is given as 22 kilometers per hour. If we divide this by 3.6, so we change it, we convert it to meter per second. And then at the beginning, the elevator starts from 0. So it will, at the beginning, it's at rest, and then it starts to move. So the initial velocity is 0, plus the acceleration, which is 1/4 g, where g is 9.81, multiplied by the time. So the time it takes between the initial velocity, which is 0, to the final velocity, which is 22 kilometers per hour. If we calculate the time for the acceleration period, you will find that the t sub a stands for time for acceleration is 2.49 seconds. We can here find also that the deceleration time is the same, exactly the same, because the value here 1/4 g is the same either in the acceleration period or the deceleration period. The final and the initial velocities, they are similar because for in the deceleration part, the final velocity is 0, the initial velocity is 22. So we get exactly the same time. So the time period for the acceleration is 2.49 seconds. The time period for the deceleration part is 2.49 seconds. We can here also calculate the displacement, the position of the elevator during the acceleration. So the acceleration displacement can be calculated using this equation. V squared is equal V naught squared plus 2a, which is the acceleration multiplied by s sub a. S sub a is like the acceleration displacement. The final velocity here in the acceleration part is 22 kilometers per hour divided by 3.6 to have it in meter per second, and this is squared is equal to v0, which is 0, initial velocity is 0, plus 2 multiplied by the acceleration, which is 1/4 g, multiplied by the displacement. If you calculate the displacement here, you will find that the elevator takes around 7.61 meters to reach the constant speed of 22 kilometer per hour when it starts from rest. You will find that because everything is the same between the acceleration and deceleration. So even if you calculate the displacement, the deceleration displacements, it's going to be exactly the same value, which is 7.61 meter. The cruise displacement, which is in between, so we have acceleration, then cruising, and then deceleration. So we found the acceleration displacement, the deceleration displacement. So now we can find the cruise displacement. The cruise displacement is S sub C, which is 350, the total run of the elevator, minus S sub A, which is the acceleration displacement, minus S sub D, which is the deceleration displacement. So we have here 335 meters. During the 335 meters, the elevator would move with a constant speed of 22 kilometers per hour. Where we can find the cruise period using just the velocity, standard velocity equation. The velocity is equal to the displacement divided by the time. So we can find here the time, T sub C is equal to the displacement, the cruise displacement, which is 335, divided by the cruise speed or velocity, which is 22 divided by 3.6 in meter per second. So it's equal here, the period for the cruise is 54.8 seconds. So the total run time is the time required for the acceleration, for the cruise, and for the deceleration. We found that the time required for the acceleration is 2.49 seconds. The time required for the cruise is 54.8 seconds, and the time required for the deceleration is 2.49 seconds. So the total time, the total run time for the elevator is 59.8 seconds, about 1 minute. So this is problem number 2. We have here the cart, this cart here. The cart impacts the safety barrier. So we have a barrier here, a safety barrier, and the car impacts the safety barrier with an initial speed of 3.25 meter per second. So the initial speed of the cart is 3.25 meter per second and is brought to a stop by the nest of nonlinear springs, which provide a deceleration A equals negative k sub 1x minus k sub 2x cubed, where x here is the amount of spring deflection. So in the end, this cart will stop, so the final velocity is going to be 0. And during the initial period and the final situation of the cart, it's going to have some deceleration according to this equation. So the x here is the amount of spring deflection. You can see on the figure here, x is measured from here. So when the cart hits this barrier, so it will move to the right, and then using these springs will just decelerate the cart, but it will deform as well in the x direction. And this is the undeformed shape before the cart hits the springs. So where x is the amount of spring deflection from the undeformed position, and k1 and k2 are positive constants. So we have the two positive constants here, k1 and k2. If the maximum spring deflection is 475 millimeters, so it means that the maximum deflection is corresponding to a velocity of 0, because if the springs are compressed to this maximum position, so the cart would have stopped at this point. And the velocity at half maximum deflection, so at half maximum, if this is the maximum deflection, if you divide this maximum deflection by 2, it's going to give you the position where the velocity is 2.84 meter per second. So the velocity is given at the mid position of the maximum. So determine the values of the corresponding units for constant K1 and K2. So we require to find K1 and K2 and their units, the values and their units. So let's start with what is given here. So the initial velocity of the cart is given as 3.25 meter per second. The maximum deflection of the springs is given as 475 millimeters. The velocity in the middle or in the mid of this x max is given as 2.85 meter per second at x is 1/2 x max. 1/2 x max is just this number divided by 2. The acceleration here is given as a function of displacement, so we need to use this equation like v dv is equal to a dx. So we call the acceleration here, the displacement here x rather than s. So v dv is equal to the acceleration, which is given by this equation, negative k1x minus k2x cubed multiplied by dx. So we can integrate the left and the right hand sides here, and because we are given the initial velocity, so it's between v0 to v, and the undeformed shape is at the beginning is 0, so x0 is 0 to any value x of this acceleration value that is given it as a function of displacement. So the integration of v is v squared divided by 2. So and when we just plug in the values for the limits of the integration here, we have on the left hand side 1/2 v squared minus v0 squared. On the right hand side, we can integrate this part. So the integration of x is x squared divided by 2. So we have here negative k1 divided by 2 multiplied by x squared. And the integration of x cubed here is x to the power 4 divided by 4. So we have here minus k2 divided by 4 multiplied by x4. And this is our equation, equation number 1. So again, we are just repeating the equation number 1 here. And we have two conditions, obviously, and we have two unknowns. It means that we are getting two equations into unknowns, we are solving them together, and that's it. So the first condition was given as the x maximum is given as 0.475 meters. We just multiplied this by 10 to the power minus 3 to convert it to meters. And at the maximum position, so the car velocity is 0. So the final velocity is 0. So if we take these two values and plug them in here in this equation, so we have 1/2, which is this, multiplied by the final velocity, that is 0, the negative minus the initial velocity squared, 3.25 meter squared, is equal to negative k1 divided by 2 multiplied by the displacement, which is maximum here, 0.475 squared, minus k2 divided by 4 multiplied by the displacement to the power 4. You see here that this equation, we have two unknowns. We have k1 and k2. So we still need one more equation. So if this is our equation number 2, so we still need one more equation to solve for the k1 and k2. The second condition was that at the mid maximum displacement, which is x max divided by 2, at this displacement in meters, the velocity of the cart was given as 2.85 meter per second. So going back to equation number 1, then just let's substitute with this equation. So the final velocity at this in the middle, it was 2.85 squared, so 1/2 multiplied by 2.85 squared, minus the initial velocity, which is 3.25 squared, is equal to negative k1 divided by 2 multiplied by the displacement. Remember that the displacement here in the middle, so we just need to divide the maximum displacement by 2 here, and then substitute it here as well in the last part, which is 0.475 divided by 2 to the power 4 multiplied by k2 divided by 4. So we have equation number 3. So all what we need to do now is just to solve equation number 2 and equation number 3 together to get the value of k1 and the value of k2. And just in order to define the units for k1 and k2, you just need to remember that the right hand side here is equal to the acceleration. It means that or it is equal here to the velocities. So if you look at the equation number 1 here, you will find that on the left hand side you have velocity squared. So if the velocity here is in meter per second, and because it's squared, so meter squared per second squared, so each term on the right hand side here must be meter squared per second squared. So for example, let's talk about the first term. So x here is displacement. If it is in meters, so it's going to be x squared in meter squared. So in order to have this term as meter squared per second squared, so k1 must be in second to the power negative 2. Okay, and the same is here. So we have meter to the power 4 here. So we must have k2 in meter to the power negative 2, second to the power negative 2. If you multiply these two values by meter to the power 4, which is this one, you will have the meter per second squared, which is the velocity squared. Our third problem here, which is for a certain interval of motion, the pen A. So we have a pen here. This pen follows a parabolic slot in this plate here. And we have the origin here. We have the x-axis. We have the y-axis. We have the pen at point A. And this curve, this parabolic curve, is defined as x is equal to y squared divided by 60. And the pen here is controlled by the vertical motion of this part in the middle of this horizontal slotted arm. So when we rotate these two screws, so the arm goes up and down, and because the pen is here, so the pen moves with the arm up and down, and because of the slotted arm here, so the pen can easily follow the slot, the parabolic slot on the plate, the vertical plate over there. So for a certain interval of motion, the pen A is forced to move in the fixed parabolic slot by the horizontal slotted arm, which is elevated in the y direction at the constant rate of 30 millimeter per second. So we see that the arm here moves in the vertical direction with a specific speed, with a constant speed. And because it takes the pen with it when it moves in the y direction, so the velocity of the pen in the y direction is the same as the arm. So the velocity of the pen in the y direction is the same as the arm, which is 30 millimeter per second. So if we define the velocity in the x direction as x dot and the velocity in the y direction as y dot, so the y dot for the pen is 30 millimeter per second. All the measurements here are made in millimeters and seconds, and we are required to calculate the velocity v, so the velocity v and the acceleration a of the pen. So we need to find the total velocity v, the total acceleration a of the pen, when the x is equal to 60 millimeters. So remember that the x can be measured from here in the horizontal direction, but because we have the equation here, so if x is given as 60, we can also find y. So what is given here? We have been given the velocity in the y direction, which we call it x dot, so it's 30 millimeter per second. Because it's constant, so if we get the acceleration in the y direction, it's going to be 0. We've been given the equation, x is equal to y squared divided by 60. So based on this equation, we can find both the velocity x dot, the acceleration x double dot. These are the components of the velocity and acceleration in the x direction. But here is just, we need to use the chain rule, obviously, because x dot is dx by dt, and here the x is not directly function of the time, it's function of y. So we need to use the chain rule. So on the left hand side, we just differentiate with respect to t. So dx by dt, which is x dot, is equal to, on the right hand side here, we cannot differentiate with respect to time. We just need to differentiate with respect to y first, and then we differentiate y with respect to t. So it's dx by dy multiplied by dy by dt. dy by dt is nothing but y dot. So we can consider this as y dot. So, and the left-hand side here, dx by dt is x dot. So x dot is equal to dx by dy multiplied by y dot. So if we can get the dx by dy, so we get the equation. So the dx by dy just can be found using this equation. So the dx by dy is just nothing but 2y divided by 60. So because 60 is constant and y squared, the differentiation of y squared with respect to y is 2y. So we have here x dot on the left-hand side is equal to the differentiation of x with respect to y, which is 2y divided by 60, and this part is y dot. So in the end, we have here x dot as y divided by 30 multiplied by y dot. So in order to find x double dot, which is the component of the acceleration in the x direction, we need to again get the differentiation, the time derivative of this equation. But the problem is even more complicated because on the right-hand side here, we have two variables. Y is a variable and y dot is another variable. So we need to use the product rule. We need to use the product rule here. So on the left-hand side, if we get the derivative here of this part with respect to time, so it's going to be x double dot. And here we have the first variable. We use the product rule. So we take the first variable, which is y divided by 30, multiplied by the derivative of the second variable. The time derivative of the second variable is y double dot, plus the second variable, which is y dot, multiplied by the time derivative of the first variable, which is y dot divided by 30. So we've got here y dot as 30, we've got y double dot as 0, and we've got here y dot as an equation, and we've got x dot as an equation and x double dot as an equation. So we have the components now of the velocity and the acceleration in the x and y directions. So it was given in the problem that all the calculations have to be made at x is equal to 60 millimeter. Remember that there is a relation between x and y, so using the equation we can get y as the square root of x squared, then y is going to be 60 millimeter as well. And then because we have y and x here, and we have y dot as 60 millimeter per second, and we have y double dot as 0, so we can here start finding all the components for the velocity and the acceleration. So for example, x dot here is, as found previously, is y divided by 30 multiplied by y dot. The y value here is 60. So 60 divided by 30 multiplied by y dot, which is given 30. So we have here x dot is 30 as well. So now we can calculate x double dot. X double dot was found using this equation. So y divided by 30 multiplied by y double dot plus y dot multiplied by y dot divided by 30. So the y value is 60 divided by 30 multiplied by y double dot is 0 because the velocity in the y direction is constant, plus y dot is 30. It's given y dot is 30 is given divided by 30. So this gives us 30. This cancels with this. So we end up here with the x double dot as 30 millimeter per second squared. And now we can calculate the velocity and the acceleration, the total velocity and the acceleration, where the velocity is the square root of x dot squared, x component squared plus y component squared. The x component squared here is 60. The y component is 30. So 60 squared plus 30 squared is equal to 30 square root of 5 millimeter per second. The acceleration is the square root of x double dot squared plus y double dot squared. The x double dot squared is 30. We found it here. So it's 30 squared plus the y double dot is 0. So we have here 30 millimeter per second squared. So I've got now the total velocity and the acceleration of the pen when the x is equal to 60 millimeter and y is equal to 60 millimeter. We have the fourth problem. So in here, we have the particle P. So we have a particle P here. Okay. So it starts from rest at point A. So at point A, this particle starts from rest. So the velocity of the particle at point A is equal to 0. And the time is equal to 0, of course. And changes its speed thereafter at a constant rate of 2g as it follows the horizontal path shown. So it means that the particle between point A and point B, the particle has an acceleration of 2g. Okay, so the acceleration is constant between point A and point B, and then it's 2g, and the distance here is 3 meters. Determine the magnitude and direction of its total acceleration. So the total acceleration is required as a magnitude and direction in 3 different cases. Just before it passes point B. So just before it reaches point B, what is the magnitude and direction of the acceleration of the particle P? Just after it passes the point B, so immediately after it passes here at any point here, point B, so what is the total acceleration and the direction? As it passes point C, so at point C as well, so point C before and after point B. State your directions relative to the x-axis. So the x-positive direction is given here, and it says here, consider that the counterclockwise is positive. So if we are measuring the angle, so the counterclockwise direction starting from x is positive. So from here going up, so this is our positive direction for the measuring the angle. You see here that the radius here is constant as well, and it's 3.5 meters. So the first part, it asks us to find the acceleration, the direction, and the magnitude of the total acceleration before it reaches point B. So obviously, between point A and point B, the acceleration is constant, and this was explicitly given in the problem. Says that the acceleration is equal to 2g, so it's 2 multiplied by 9.81 is equal to 19.62 meter per second squared. And because it's horizontal, so the angle here is 0. So the total acceleration is 19.62, and the angle is 0. This is between point A and point B. So in this case, between point A and point B, we consider that this is just rectilinear motion, so it moves in a straight line. But when it reaches here and follows this curve, we can use the normal tangential coordinate system to study the particle motion along this curve here. So it means that in order to find the total acceleration, we are required to find the tangential acceleration and the normal acceleration. And the normal acceleration is between the particle to the center of rotation, and here it goes towards the center of rotation, and the radius of curvature here is given as 3.5. So at this point P, the tangential acceleration, which is horizontal in this case, is given as 19.62. And all what we need to do is just to calculate the normal acceleration. So in order to calculate the normal acceleration, we want to get the velocity of the particle at this point P. And this is what we'll be doing. So we need to find the velocity of point P at this point. So again, just going back to study the motion of the particle between point P and A. So Vp squared, which is the final velocity squared, is Va squared plus 2 multiplied by the acceleration multiplied by the distance between B and A. The distance between P and A is given as 3. So the Vp squared, which is unknown, is equal to the initial velocity, which is 0, plus 2 multiplied by the acceleration. So the acceleration between A and B is constant, and it's 19.62 multiplied by the distance, which is 3. So based on this equation, we can find the velocity at point B, which is 10.85 meter per second. So the normal component of the acceleration in this case is Vp squared divided by rho. The rho here, radius of curvature, is constant between P and C, and it's 3.5 meters. And the velocity here was found as 10.85 squared. So Vp squared is 10.85 squared divided by rho, which is 3.5. So that gives us 33.6 meters per second squared, the normal component. And as I said, at point P, the tangential component of the acceleration is the same as 19.62. So you see here that the acceleration is the square root of an squared plus at squared. So this is the total acceleration. The normal component of the acceleration is 33.6 squared, and the tangential component squared is 19.62 squared. So we have here 38.9 meters per second squared. So this is the total acceleration of the particle at point P, just immediately after point P. Here we can also find the direction. So the direction is tan inverse the normal component divided by the tangential component, which will give us 59.7. So if this is the particle at point P, so we have the tangential component of the acceleration going to the right, and the normal component going to the center of rotation or center of curvature. And this is the normal component, this is the tangential component. So the total is going to be direction. And the angle theta is here. Remember that it was required in the problem to get the value of the angle measured from x, considering that the counterclockwise is positive. So because we are measuring, if we consider that this is x positive, so we are measuring the angle in this direction. So that's why we should say here it's negative 59.7 measured from the x positive direction and considering the counterclockwise as the positive direction. And now considering the third and final position where the particle reaches point C. So at point C, again, we would apply the normal tangential coordinates. But in order to find the normal component of the acceleration, we need to find the velocity. So we can still measure, the acceleration is constant, so we can still measure the velocity or calculate the velocity based on the information given at point A. So we say that the velocity at point C squared is equal to the velocity at point A squared plus 2 multiplied by the tangential acceleration. So the tangential acceleration here is constant because it's only, it just moves only under a constant force, which is the weight. So we don't have any changing forces here. That's why the acceleration, the tangential acceleration, is going to be constant. Plus 2 multiplied by the acceleration, multiplied by the distance between SC and SA. So the VC squared, which is the velocity at point C squared, is equal to the initial velocity squared, which is 0, plus 2 multiplied by the acceleration, the tangential acceleration, which is 2g, it's 19.62, multiplied by the distance between A and C. This is the part we need to go back here to show it. So the distance between C and A, so it's the length of this part of the curve, and then this distance. So it's 3 meters plus 1/4 here of a circle. So it's r theta. So the theta here in radians is pi divided by 2, and the r is 3.5. So the total distance is 3 meters plus 3.5, which is the r multiplied by the angle in radians, which is pi divided by 2. So this is the distance between C and A, 3 meters plus 3.5 multiplied by the angle in radians is pi divided by 2. Based on this equation, we get the velocity C. VC is 18.26 meters per second. Now, because we have the the radius of curvature, we have the velocity, we can calculate the normal component of the acceleration. So a sub n, which is the normal component of the acceleration, is vc squared divided by rho. So the velocity here is 18.26. vc squared is 18.26 squared divided by rho, which is 3.5. So we're getting here 95.3 meter per second squared. So the total acceleration is the square root of an squared plus at squared, where the an is 95.3 and the at is 19.62. So in this case, the total acceleration is 97.3 meter per second squared. And again, we can calculate the angle as the tan inverse, the normal component of the acceleration divided by the tangential component of the acceleration, which will be 78.4. But let's just measure this. Let's just draw this to understand how we can measure the angle with respect to the x positive direction. So at this case, we have the tangential component of the acceleration going down, because at point C, the tangential component is tangent to the curve, so it's going down. And then the normal component is going towards the center of curvature, so it will be going in this direction. So the total acceleration is going to be in this direction. And the angle is between the total acceleration and the tangential here. So we take the tan, this component, which is 95.3, divided by this component, so the angle is here. But if we wanted to measure the angle with respect to x-axis, which is in this direction, so we need to add this angle, which is 90. So and of course, because it's in the clockwise direction, so it's going to be all negative. So we consider that this angle is negative first, and then we add negative 90 to this. So we have the angle measured from the x-axis in the clockwise direction as a negative 168.4 degrees. Here is your last example where we have a part here called OP, and we have a screw, and we have a collar, and then we can control the motion or the rotation of this arm using the screw. So we can, by moving the screw, by rotating the screw moves the collar forward and backward, and then this pin slides up and down, and then at the same time it rotates the arm OA. They call the arm, the total arm is OA. Okay, so the rotation of the part OA is controlled by the lead screw, which imparts a horizontal velocity V to the collar C. So we have here, when we rotate the screw, so it's just a knotted screw. So the collar here is just a knot. So it just moves forward and backward. So, and it applies a velocity V in the horizontal direction to the pin B. So we have here a rotation of bar OA is controlled by the lead screw, which imparts a horizontal velocity V to the collar and causes pin P to travel along the smooth slot. So the pin here can go up and down with the motion. So determine the values of R dot, theta dot. So he's asking us about R dot and theta dot. It means that we must use the polar coordinate system R and theta. So where the R value, which is the distance between O and P, this is the R value, and if the H is equal to 160, so this distance here, this height is 160 millimeter, and the horizontal distance X here is given as 120 millimeter. They are given to be able to calculate the angle theta. And the V, the velocity, is given as 25 millimeter per second. So what we can do here, we just say, okay, H is given, X is given. So by the Pythagorean theorem at this position, we can calculate R, right? So R here is the square root of 160 squared plus 120 squared, which is 200. And then we can also calculate the angle theta. We can calculate the sine and the cosine of angle theta. Why? Because if we look here, the velocity is horizontal. The total velocity was given as horizontal. If we consider that this is our radial direction, so this is our direction, this is R now, and the perpendicular direction to that is theta. So it means that we have along the R direction here, we have a component called VR, and along the theta, we have another component called V theta. So, and the angle between these two, by just simple calculations, we find that this angle theta is the same as this angle theta. And the velocity here is given as 25 millimeter per second. Based on the triangle, we can find that sine theta is 120 divided by 200, and the cosine theta is 160 divided by 200. So we can find the cosine and sine theta. So going back to the resolution of the velocity here, we see that VR, which is obviously based on the radial, the polar coordinate system, or r theta coordinate system, VR is equal to r dot. So, and r dot here is equal to VR. Can we find VR as a function of V? Yes, because V here is the total velocity. So this component is V cosine theta, and this component is V sine theta. So VR here is eventually V sine theta. We have the value of V, which is given as 25 millimeter per second. Sine theta is 3 divided by 5. So if we multiply this, we are getting 15 millimeter per second. So VR, which is R dot, is equal to 15 millimeter per second. So R dot is found now. So if we go to the second component, if we calculate the second component, V sub theta is equal to V cosine theta. So the V sub theta in the R theta coordinate system is equal to R theta dot. So R theta dot is equal to, based on this resolution, is equal to V theta, where V theta is V cosine theta. So the V is given, cosine theta can be found from the triangle as 4 divided by 5. So we get here R theta dot is equal to 20. So if R multiplied by theta dot is equal to 20, and R, we've calculated R as 200, so this means that theta dot is equal to 20 divided by 200, so which is 0.1 radian per second. So this is the end. Thank you so much. I hope this was helpful. Thanks.